Hello, learners. Today we are going to see an important topic in condensed matter physics, that is, simple crystal structures. I'm Dr. N. Sudha, working as an associate professor in Department of Physics, Sri Sharda College for Women, Salem. Matter consisting of one or more elements or their chemical compounds exists in nature in the solid, liquid, and gaseous states. As the atoms or molecules in solids are attached to one another with strong force of attraction, the solids maintain a definite volume and a definite shape. Furthermore, the solids can be classified based on size, atomic arrangement, chemical nature, and physical properties. The solids may be broadly classified as crystalline solids and amorphous solids. In the crystalline solids, there are ionic crystals, covalent crystals, molecular crystals, metal crystals, and atomic solids. The crystalline states of solids is characterized by regular or periodic arrangement of atoms or molecules. Most of the solids are crystalline in nature. This is due to the reason that energy released during the formation of ordered structure is more than that released during the formation of disordered structure. Thus, crystalline state is a low energy state and is therefore preferred by most of the solids. The crystalline solids may be subdivided into single crystals and polycrystalline solids. In single crystals, the periodicity of atoms extends throughout the material, as in the case of diamond or quartz or mica. A polycrystalline material is an aggregate of a number of small crystallites with random orientations separated by a well-defined boundaries. The small crystallites are also known as grains, and boundaries are grain boundaries. It may be noted that although the periodicity of the individual crystallites is interrupted at grain boundaries, yet the polycrystalline form of a material may be more stable compared with single crystal form. Most of the metals and ceramics exhibit a polycrystalline structure. The amorphous solids, or the non-crystalline solids, are characterized by the completely random arrangement of atoms or molecules. The periodicity, if at all present, extends up to a distance of few atomic diameters only. In other words, these solids exhibit short range order. Such type of materials are formed when the atoms do not get sufficient time to undergo periodic arrangement. Glass is an example of amorphous materials. Most of plastics and rubbers are also amorphous. Properties are the way the material responds to the environmental and external forces. The various properties may be as that of the mechanical properties, electrical and magnetic properties, thermal properties, optical properties, and chemical properties. To understand a crystal, we should know what are lattice points and unit cell. A space lattice is defined as an infinite array of points in three dimensions in which every point has surroundings identical to that of every other point in that array. The unit cell is the smallest unit, which, when repeated in space indefinitely, generates the space lattice. The intercepts A, B, and C are called as the primitives or the cell primitives. And the angles alpha, beta, and gamma are known as the interfacial angles. The primitives ABC and the interfacial angles alpha, beta, and gamma are the basic lattice parameters. So, the unit cell formed by the primitives ABC is called as a primitive cell. The primitive cell will have only one lattice point. All the primitives are unit cells, but it is not necessary that the unit cell should be a primitive cell. A crystal structure is obtained by combining the space lattice and the basis. The basis provides the number of atoms per lattice point, their types, mutual orientations, and distances of separation. So, what defines a crystal? The 3D periodicity. Anything with maybe an atom or a molecule that present at some point in space repeats at regular intervals in three dimensions defines the crystal. So it is the periodicity of the repetitive atoms or molecules which contribute to the crystal. So it can be of either of this type. So we can very well see here the periodicity of different types of crystals. So what is a lattice? A lattice is a set of points with an identical environment, and it is a primary building block for any crystal. So when this building block repeats in the same fashion, we can get a wonderful crystal. So crystal is a solid composed of an object or a motif repeated translationally on the 3D lattice. The period of repeat in each of the 3D lattice direction is described by the unit cell. So we can very well see here motif. This is the unit cell which is repeated and forms the lattice, and this is the beautiful structure of a crystal. In order to understand the crystals completely, we should take the X-ray diffraction method. X-rays, being electromagnetic radiation, also undergo the phenomenon of diffraction as observed for visible light. However, unlike visible light, X-rays cannot be diffracted by ordinary optical grating because of their very short wavelength. In 1912, a German physicist, Max Worley, suggested that the use of single crystal to produce diffraction of X-rays. Since the atoms in a single crystal are regularly arranged with interatomic spacing of order of few angstroms, a crystal can act as a three-dimensional natural grating for X-rays. In 1912, W. H. Bragg and W. L. Bragg, both father and son, put forward a model which generates the condition for diffraction in a very simple way. They pointed that a crystal may be divided into various sets of parallel planes. The directions of diffractions can be accounted for the X-rays considered to be reflected by such set of parallel atomic planes followed by constructive interference of resulting reflected rays. Thus, the problem of diffraction of X-rays by the atoms was converted into a problem of reflection of X-rays by the parallel atomic planes. Hence, the words refraction and reflection can mutually be interchanged in Bragg's treatment. Based on these considerations, Bragg derived a simple mathematical relationship which serves as a condition for Bragg reflection to occur. This condition is known as Bragg's law. To obtain the Bragg's law, we have to consider a set of parallel atomic planes with interplanar spacing d and having Miller indices HKL. Let a parallel beam of X-rays of wavelength lambda be incident on these parallel planes at glancing angle theta, such that the rays lie in the plane paper. So we can consider two such rays which strike onto the planes, get partially reflected, and at the same angle theta according to Bragg's statement. We know here that the only constructive interference is formed, and because of that, we can find the interplanar spacing d is equal to n lambda by 2d sine theta. This equation is known as Bragg's law. There are only 14 distinguishable ways of arranging points in the three-dimensional space. The 14 space lines are known as Bravais lattice. A Bravais lattice is a three-dimensional arrangement of points that describes how atoms are arranged in the crystals. So the key characteristics are each point in Bravais lattice is called as lattice point or site. Each lattice point represents a molecule, atom, or group of atoms. The environment around each lattice point is the same. The lattice has translational symmetry. There are 14 possible 3D Bravais lattices. These lattices fall into 7 crystal systems based on rotational symmetry. The 7 crystal systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, and hexagonal. So this is the angle and the ABC values for the triclinic, A not equal to B and not equal to C. So we have in the 7 crystal systems as triclinic, monoclinic, orthorhombic, tetragonal, cubic, rhombohedral and hexagonal. Let us see each one in detail. In triclinic, not equal to B not equal to C, and alpha not equal to beta not equal to gamma, which is not equal to 90 degree. For a monoclinic system, A not equal to B not equal to C, alpha equal to gamma equal to 90 degrees, but beta not equal to 90 degrees. For the orthorhombic, A not equal to B not equal to C, whereas alpha is equal to beta is equal to gamma is equal to 90 degrees. Moving on to the tetragonal shape, it is A equal to B not equal to C, alpha equal to beta equal to gamma is equal to 90 degrees. And for the cubic system, which is the most common system for most of the crystals, A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degrees. Going on to the rhombohedral system, A is equal to B is equal to C, alpha is equal to beta is equal to gamma, but gamma not equal to 90 degrees. And then finally, the hexagonal system states that A is equal to B not equal to C, and alpha is equal to B, beta is equal to 90 degrees, and gamma is equal to 120 degrees. Now taking into the four types of unit cell, primitive, body-centered, face-centered, and side centers, for the seven crystal system, we have 14 Bravais lattice. In the cubic, there are three Bravais lattice. For tetragonal, 2, orthorhombic 4, hexagonal 1, trigonal 1, monoclinic 2, and triclinic 1. Altogether, for the seven crystal system, we have 14 Bravais lattice. So, to understand all the crystal system, we should know what is X-ray crystallography. X-ray crystallography is an experimental technique that exploits the fact that X-rays are diffracted by crystals. It is not an imaging technique. Based on the diffraction pattern obtained from X-ray scattering of the periodic assembly of molecules or atoms in the crystal, the electron density can be reconstructed. Additional phase information must be extracted either from diffraction data or from supplementing diffraction experiments to complete the reconstruction. A model is then progressively built into the experimental electron density, refined against the data, and the result is quite accurate for the molecular structure. So using the X-ray crystallography, we can understand the crystal structure to a very fine extent. Based on the functions, the materials are further classified as biomedical materials, electronic materials, LNG technology materials, magnetic materials, optical materials, smart materials, and structural materials. So, based on the function, we can use these materials for different purposes. How the world has transformed in few decades because of the materials. Materials are so important in the development of any civilization. We associate ages with the development of civilization. In the origin of human life on Earth, the Stone Age, people used to have only natural materials like stone, clay, skins, and wood. And in the Bronze Age, about 300 BC, people used only copper and how to make it harder by alloying. The use of iron and steel, the stronger material, gave an advantage around 1200 BC. The next big step was the discovery of inexpensive process to make steel around 1850 AD, which enabled the railroads and the building of the modern infrastructure of the industrial world. So because of the advent of materials and its usage and functionality, now we can see the transition of the gadgets from the transistor to pocket radio, tape recorder, CD player, DVD, iPod, and to smartphones. So these are some of the important and rare pictures of the old model computers, which was used in the beginning. Then these are the storage systems from floppy disk to mini floppy disk, CD drives to pen drives we have come now. And these are the models of modern computers. So with the advent of new materials, so we have now emerged to lightweight laptops. And in telephone also there is a big transition. This is the earlier telephones and now we are having the smartphone, everything in one hand itself. So we can use our smartphone for communication, as a calendar, for posting, for listening to music, calculator, taking the camera, and for taking down the notes as well as the timer. So, studying of materials becomes very important, and the advent of new materials helps mankind to make his work easier. So, studying the simple crystal structures becomes very important for any physicist. Thank you.